Welcome to today's deep dive. We are really thrilled to have you with us because today we are exploring a brand new state-of-the-art research paper in generative AI.
Yeah, and it's a fascinating one.
It really is. The paper is titled GAP, Graph-Based Agent Planning. And it comes to us from a pretty heavyweight collaboration, right? Researchers from Tsinghua University, Carnegie Mellon, and like several other top-tier institutions.
Exactly. And the focus of this research is entirely on fixing one of the, one of the most frustrating bottlenecks in modern computing.
Which is such a big deal.
It is. I mean, it represents this fundamental shift in how artificial intelligence handles multi-step problems.
And that is exactly our mission for this deep dive. We're going to figure out how AI agents are finally evolving past having, a one-track mind and learning to truly multitask.
Because that one-track mind is a real problem right now.
It really is. And more importantly for you, we're going to explain why this shift is about to make the AI tools you use every single day significantly faster, smarter, and just cheaper overall.
Which everyone wants, right?
Exactly. So, to really understand the problem this paper is solving, think about that feeling when you're standing in line at the grocery store.
Oh, I know this feeling.
Right. And the person in front of you is moving with this excruciating, step-by-step precision. Like, they place one apple on the belt.
Just one.
Just one. Then they watch the cashier scan it. Then they wait for it to be bagged. And only then do they reach into their cart for the second apple.
It is agonizing to watch. You just want to step in and tell them to, put everything on the belt at once so the cashier can actually work continuously.
Exactly.
Yeah.
But that lack of parallel processing is something we usually associate with human inefficiency. When we talk about artificial intelligence, we kind of assume it's immune to that.
Yeah, we assume an AI is this, hyper-optimized multitasking brain that handles a dozen things simultaneously.
But behind the scenes, a lot of the AI tools we rely on right now operate exactly like that person with the apples.
They really do. They are trapped in a strictly sequential workflow. Like, if you want an AI to solve a complex problem that requires using external tools like searching the web, querying a database, or running a Python script, the industry currently relies on two main approaches.
And both have significant flaws. Okay, let's unpack this. The first major approach is the multi-agent system, or MAS.
Yeah, so multi-agent systems are essentially like assembling a specialized committee.
Oh, a committee.
Right. You have one AI model prompted to act as the researcher, another prompted to act as the coder, and a third acting as the reviewer.
And they pass the problem back and forth among themselves.
Exactly. And while this can achieve impressive results on really complex workflows, the downside is massive computational overhead.
Which makes sense because you're firing up multiple models, having them talk to each other, and generating all this redundant communication just to, keep everyone on the same page.
And that redundant communication eats up so much processing power. Plus, the underlying language models aren't actually naturally trained to coordinate this way.
Right, they're just guessing.
Yeah, the system relies heavily on clever prompt engineering, basically tricking the models into playing their roles rather than native built-in capabilities.
Which brings us to the second approach, which is much more common for everyday consumer AI tools. Tool-integrated reasoning, or TIR.
Right, and this is often associated with the REACT paradigm, which stands for reasoning and acting.
And it uses a single AI agent operating on a very strict think, act, observe loop.
Exactly. So in a REACT system, the AI generates a thought like, I need to find the capital of France.
Okay.
Then it generates an action. It uses the search tool. Then it just pauses and waits for the observation.
The capital is Paris.
Right. And only after that observation is received does it generate its next thought.
So it's waiting, and this is where the bottleneck happens. Current TIR models are like a chef who refuses to chop the onions while waiting for the pasta water to boil.
That's a great way to put it.
They can only do one single thing at a time. Like, if a recipe calls for boiled pasta and chopped onions, a human chef naturally knows you put the water on the stove, and while it's heating up, you grab your knife and start chopping.
But a REACT model puts the water on the stove and just stands there.
Just staring at the pot.
Staring at the pot until it boils before it even looks at the onion.
Exactly.
And what's fascinating here is how much invisible waste that creates.
Oh, tons.
When a task has multiple independent parts, forcing an AI to solve them one after the other wastes precious time and computing resources.
Right.
The model simply fails to exploit the inherent parallelism among independent subtasks. And when you're paying for cloud compute by the second,
Or paying for API tokens based on how long a model runs.
exactly, that sequential inefficiency gets incredibly expensive.
So to fix the human chef's workflow, you'd give them a prep list, right? You'd tell them to look at everything they need to do today, figure out what can happen at the same time, and plan their attack.
Right.
To fix the AI's workflow, these researchers built GAP.
Graph-based agent planning. The core insight of this paper is that instead of jumping straight into step one of a problem, the AI needs to take a deliberate pause.
It needs to literally map out the entire problem first by building a dependency graph.
Exactly. And the paper outlines 3 distinct phases for how GOP does this. Phase 1 is subtask identification.
So the AI analyzes your complex query and breaks it down into atomic, bite-sized subtasks.
Yeah. Then phase 2 is dependency analysis. The AI looks at all those individual subtasks and evaluates their relationships. It asks, which of these tasks require the output of another task before they can proceed?
Right, like you can't put the roof on a house until the walls are up, so the roof is dependent.
Exactly. But the plumber and the electrician can work inside those walls at the exact same time, so they're independent.
Which makes perfect sense.
Yeah.
And that leads to phase 3, graph construction. The AI builds a directed acyclic graph, or DAGI.
Right. And acyclic simply means the graph flows in one direction. It doesn't get stuck in an endless repeating loop.
A loop would be bad.
Very bad. So this graph serves as the master blueprint. It separates all the subtasks into what the researchers call execution levels.
Okay. Execution levels.
Yeah, level 0 contains all the tasks that have 0 dependencies. They can be initiated immediately.
So those are the independent ones.
Right. Then level 1 contains tasks that rely entirely on the results from level 0. Level 2 depends on level 1, and so on.
Okay, here's where it gets really interesting. Because, graphs and execution levels sound great in theory, but I want to ensure we ground this in reality for you, the listener. Let's look at how this actually changes the AI's behavior.
Sure.
If I give this AI a tricky multi-hop trivia question, what does it actually do differently than the old models?
Well, the paper provides a great case study for exactly this. Suppose you ask the AI, what occupation was shared by John Frankenheimer and Tiffany DeBartolo?
Okay, those are 2 distinct people, so we clearly need information on both.
Right. If you give this prompt to a traditional React model, it generates its first thought. I need to search for John Frankenheimer.
Makes sense.
It searches, reads his Wikipedia page, and observes he was a director. Then it generates a new thought. Now I need to search for Tiffany DeBartolo. It searches, reads her page, and observes she was a novelist and director. Finally, it compares the 2.
Sequential.
All
Slow.
right.
The AI is staring at the pot of water again.
Right. But under the GAP paradigm, the AI first builds its graph. It identifies 3 distinct subtasks. Task 1, search John. Task 2, search Tiffany. Task 3, compare their occupations.
Okay.
During dependency analysis, it realizes task 3 cannot happen until 1 and 2 are complete. But task 1 and 2 depend on absolutely nothing.
So it drops task 1 and task 2 into level 0.
Exactly. And because they are both in level 0, the GAP system executes them in parallel. It fires off both search queries simultaneously.
Wow.
It waits for both results to come back, and only then does it move to level 1, which is the comparison task. It synthesizes the results, finds that they are both directors, and delivers your answer.
That's brilliant. Let's expand on that with a slightly more complex scenario, just to see how deep these execution levels can go. Like, if I ask an AI to plan a weekend trip to Chicago, including booking a flight, finding a hotel near Millennium Park, and giving me a packing list based on the weather.
A standard AI would do all of that one by one.
Right. But with GAP, level 0 would simultaneously launch a flight search, a hotel search, and a weather forecast search, because none of those depend on each other.
Exactly. And then level 1 would be the task of cross-referencing the available flights with the available hotels to ensure the dates and check-in times align.
Which means level 2 would be taking that aligned itinerary and combining it with the weather data to generate your final packing list and schedule.
Yes. The efficiency of that is just undeniable.
It seems almost obvious in hindsight, which is, usually the hallmark of great engineering. But knowing how to map a plan is one thing. Teaching a language model to naturally think in directed acyclic graphs is a completely different challenge.
It really is. And the researchers didn't just use a massive trillion parameter model like GPT-4 and beg it to format its output nicely using a prompt.
No, they fundamentally altered the model's behavior through rigorous training. They chose a relatively small 3 billion parameter open source model called Qwen 2.53b instruct.
Right.
And I have to push back on that choice. If massive models like GPT-4 or Claude already have the reasoning capabilities to handle complex logic, why go through the effort of training a much smaller 3 billion parameter model to do this?
Well, if we connect this to the bigger picture, this represents the frontier of where the entire AI industry is heading. We are moving toward agent foundation models.
Yep.
The realization is that exceptional agentic performance shouldn't solely depend on raw model scale. Think of a massive model, like a generalist who has memorized an entire encyclopedia. They know a little about everything, but they require immense energy to operate.
Right. Massive compute.
But a 3 billion parameter model is like a highly trained specialist.
So instead of using a supercomputer to solve a multi-hop trivia question, you use a lightweight specialist that only knows how to do one job perfectly.
Exactly. Proving that a lightweight model can achieve state-of-the-art capabilities through specialized training is vital. It makes advanced AI accessible.
Like running it locally on your phone?
Yes, allowing it to be deployed locally on smaller devices like phones or laptops, and it drastically reduces the cost of operation.
Okay, but if I'm trying to teach this smaller model to build a flawless dependency graph, I imagine I can't just give it a prompt. I'd need to show it thousands of perfect examples. So how did they generate the textbook for this specialist to study?
They used a two-stage training pipeline. The first stage is supervised fine-tuning, or SFT. This is essentially the cold start where you show the model what a good graph looks like.
Okay.
To get this training data, the researchers used a multi-agent distillation framework. They actually had GPT-4o synthesize thousands of dependency-aware reasoning trajectories.
Oh, wow. So they gave the massive model a complex question and asked it to explicitly lay out the parallel and sequential steps, effectively creating an answer key.
Exactly. They generated about 7,000 highly curated traces based on existing multi-hop question answering datasets.
But they didn't just dump that raw data into the small model. The filtering mechanism they used is where the magic really happens.
Yeah, they were very careful.
The paper outlines 3 specific filtering criteria for this dataset, which reveal exactly what bad habits the researchers were trying to avoid teaching the new model. First was a complexity threshold. They threw out any training sample that required fewer than 3 search operations.
Because if a question only needs 1 or 2 searches, it doesn't actually benefit from parallel retrieval.
Right.
You don't need a complex project management graph to buy a single apple. They only wanted the model to study genuinely complex, interwoven dependencies.
Which is smart. Second was task diversity. They enforced a strict 6-to-4 ratio between tasks that use parallel retrieval and tasks that use sequential retrieval.
Because the AI still needs to know how to wait.
Yeah.
If every single training example shows parallel execution, the model might learn to just execute everything at once, even when a strict dependency exists.
It'll try to put the roof on before the walls are built.
Exactly. It needs to know that sometimes you genuinely do have to wait. That 6-to-4 ratio ensures the model generalizes across different types of problems.
And the third filter was a length constraint. They capped the token length of the training traces at around 2,000 tokens, discarding anything longer.
Right, because if a trace is excessively long, it usually means the AI got lost in the weeds or the search results were just full of irrelevant noise.
And feeding that to the small model would teach it to be redundant and wordy.
Which you don't want. The goal is maximum retrieval efficiency.
So after the supervised fine-tuning, the 3 billion parameter model knows how to draw a graph. It understands the formatting, but that's just stage 1. It just knows how to imitate the answer key. To actually optimize its reasoning, it needs practice.
Yes. And that requires the second stage, end-to-end reinforcement learning. They use a specific framework called DIPO, which stands for Direct Preference Optimization, to fine-tune the model further.
And DIPO is a really interesting choice here compared to traditional reinforcement learning.
It is. Traditional reinforcement learning often requires building a complex secondary reward model that constantly judges the AI's intermediate steps.
It's like a teacher hovering over a student's shoulder, correcting their handwriting while they solve a math problem.
That's a great analogy. DAPO is much more straightforward. You just present the model with a problem, let it generate a solution, and optimize it based directly on the preferred outcome.
And the reward function they use during this DPO stage is brilliant in its simplicity. It is purely based on correctness. It's a binary metric. A score of 1 if the final answer is right and 0 if it's wrong.
They don't give the AI partial credit for formatting the graph nicely. They don't penalize it for using a certain syntax.
Right, because the first stage already baked in the format consistency.
Exactly. So the reinforcement learning stage focuses entirely on outcome-driven optimization. The AI is essentially told, I don't care how you organize your workflow, just get me the right answer.
And because the AI wants that reward of one, it naturally learns to balance the trade-offs between parallel exploration and its own context window limits.
Right. It figures out the absolute fastest, most efficient graph to reach the correct answer.
So the model is built, the graph framework is implemented, and the two-stage training is complete. The ultimate test is whether this 3 billion parameter specialist actually beats the current state-of-the-art models out in the wild.
And the results are impressive.
So what does this all mean? Let's look at the benchmarks, because there's a clear delta here. The researchers tested GAP against current top tool-augmented methods, specifically using a model called Search R1 as their primary baseline.
And Search R1 is important context here. It is a highly optimized navigation model designed specifically to retrieve information across multiple documents.
It's basically the reigning champion of complex searching.
It is, but it operates sequentially. So beating Search R1 means proving that a lightweight graph model can outperform a dedicated, heavyweight sequential powerhouse.
And it did. Across multi-hop question answering datasets, GAP outperformed the best baseline by an average of 0.9% in raw accuracy.
Which, a 0.9% bump in accuracy is solid, but the true victory of the GAP paradigm isn't just the accuracy. The real story is the sheer efficiency it brings to the table.
Oh, totally. Let's look at interaction turns, how many times the AI has to stop, think, and query a tool. On the 2-wiki multi-hop QA dataset, traditional Search R1 took an average of 3.05 turns to solve a problem. GAP dropped that to 2.03 turns.
That is a 33.4% reduction in interaction turns.
Which is huge.
It is. And fewer turns directly translate to faster execution times. On the Hotpot QA dataset, the total time cost to run a batch of data dropped from 248 seconds with the baseline down to just 168 seconds with GAP.
Wow.
That is a 32.3% reduction in time.
It also uses fewer words to accomplish the goal, right? On Hotpot QA, the average response length shrank from 554 tokens down to 416 tokens, a 24.9% reduction. The AI just gets straight to the point without rambling.
And this brings us to a crucial metric called the cost of pass. This is a framework for evaluating language models that represents the expected monetary cost to get a correct solution.
Okay.
It calculates the cost of a single inference attempt based on input and output tokens and divides it by the success rate.
Let's translate what this cost of pass metric actually means for you, the listener, in your daily life. If you're using an AI agent to prep for a major client meeting or to synthesize a dozen research papers for a project, you don't want the AI spinning its wheels.
Racking up API token costs?
Exactly. Racking up costs and taking 3 minutes to generate a rambling answer.
You need a tool that operates with minimum friction.
Shorter responses, fewer interaction turns, and higher accuracy mean a massive reduction in that cost of pass. It means getting exactly the knowledge you want, significantly faster, and without all the information overload.
The GAP paradigm proves that we don't necessarily need bigger and bigger AI models, consuming the power of a small city, just to achieve better reasoning.
We just need models that know how to organize their thoughts.
Yes. Models that can map their own dependencies and execute parallel tasks like a master project manager. It shifts the architecture of problem solving from a reactive, step-by-step stumble into a proactive, strategic orchestration.
It's a complete reimagining of the AI workflow.
This raises an important question, though, as we look to the future.
Oh.
The benchmarks tested in this paper, like Hotpot QA and 2Wiki, are primarily academic text retrieval tasks. The next major frontier is seeing how this graph-based parallel efficiency scales to truly open-ended, complex, real-world web navigation.
Now imagine an agent autonomously navigating the live internet to book a multi-city flight, cross-reference hotel availability, and check your calendar all in parallel.
Reacting to live website changes as it goes.
That is the ultimate goal for consumer AI. And it leaves us with one final, slightly provocative thought to chew on before we go.
Okay, let's hear it.
If a lightweight 3 billion parameter AI can now autonomously construct a flawless dependency graph to perfectly optimize its own workflow in mere milliseconds.
Wow, yeah.
How long until we unleash these exact same agents to analyze and optimize the dependency graphs of our own human lives?
That's a wild thought.
Right. Will the ultimate use case for this technology be the AI stepping in as the project manager for our daily routines, looking at our schedules, finding our bottlenecks, and telling us exactly which tasks we need to be running in parallel?
I could definitely use one of those.
I think we all could. Thank you for joining us on this custom-tailored deep dive into the GAP framework. Keep questioning the bottlenecks, keep looking for the parallel paths, and most importantly, keep seeking out those aha moments. Until next time.